Lesson 86. You will begin this lesson with an investigation found on page 550 in your textbook. Notice how in question 5, there is or may be a typo in the version of the textbook that you have. And instead of finding the limit as x approaches 0 of the function, you're looking for x approaches pi. Okay, so make sure you pay attention to that so that you can make a comparison between what you get from part 4 and 5. In the next little bit, I'm going to just work out the different parts so that you can check your answers to the investigation. I also encourage you to pause the video, do the questions yourself before looking at the answers, all right? From the investigation, we work on functions that take on indeterminate forms like 0 over 0 and infinity over infinity, so to speak. And what we notice is that by taking the limit of the derivatives of these functions instead of, f of g over g of x, we take the limit of f prime over g prime, we still arrive at the same result as what the graph shows us. So it's proven that this is a very helpful method for evaluating any limits in indeterminate form. And this rule that we have just explored is called L'Hopital's rule. Now we're going to look at some examples of L'Hopital's rule. And remember that in the card it outlines when we can apply L'Hopital's rule is when you have the limit of a quotient that results in indeterminate form, like 0 over 0 or infinity over infinity, okay? Example 1. Use L'Hopital's rule if possible to find the following limits. So question A, we have cos x over pi minus 2x when x approaches pi over 2. So let's do a quick check here. Cosine pi over 2 is 0. Pi minus 2 times pi over 2. So pi minus pi, it is 0. So we do have indeterminate form. That means we should be taking the derivatives of both the numerator and the denominator now. So cosine x turns into negative sine x. In the denominator, pi is 0. And then the derivative of negative 2x is negative 2. So we're taking the limit as x approaches pi over 2 of sine x. And then multiply that by a half. And then this is going to be half. Okay? B. Here we have the limit as x approaches infinity for ln x over x. What do you think? Ln of x near infinity is infinite. X infinite. Again, we have indeterminate form. So now let's apply L'Hopital's rule. Derivative of ln x, 1 over x. Derivative of x, 1. Now I have 1 over a number that is very, very, very close to infinity. So we're not really dividing by infinity, but we know the result will be very small, close to 0. Okay. Here is example 2. So in this question, we have the limit as x approaches 0 of this difference of 1 over sine x minus 1 over x, I can write that as a single expression. So x sine x as a common denominator, x minus sine x in the numerator. Okay, so let's check. Putting 0 as x, I have 0 minus sine 0, 0. I have 0 times sine 0, also 0. So this is just notes on the side, okay? So now we will take the derivative of this function. So 1 minus cos x. I need to use the product rule in the denominator. So derivative of x is 1 times sine x. And then plus x, derivative of sine is cos x. Let's check if I can evaluate this limit. Cosine 0 is 1. So I have 1 minus 1 at the top. Sine 0 is 0, 0. I still have indeterminate form. Well, what if I take the derivative of both functions again? I will have 0 minus negative sine, so sine x. At the bottom, I have cosine plus product rule, cos x minus x sine x. Now what? Sine of 0 is 0. Cosine 0 plus cosine 0. 1 plus 1, 2 minus 0. So now I do not have indeterminate form, but this still gives me 0 over 2, which is 0. Okay? Use L'Hopital's rule if possible to find any horizontal asymptotes of the function y equals to the square root of x squared plus 2x minus x. Okay. So L'Hopital's rule is suggested here, but we don't see a rational expression. Let's start by setting up, the expression for calculating horizontal asymptote, which really is to take the limit as x approaches infinity for x squared plus 2x in the square root minus x. It seems like the limit doesn't exist here, because if I simply, imagine putting infinity into x's, the number gets really big. But is that really the case? Well, let's do something that we're actually quite familiar with by multiplying this rational expression here, the conjugates, just like how you would be rationalizing denominators, okay? So what does this give us? I have limit as x approaches infinity. I have a difference of squares in the numerator. So x squared plus 2x minus x squared over bottom is just x squared plus 2x plus x. Okay, let's simplify this. I have limit as x approaches infinity, 2x at the top, and then x squared plus 2x in square root plus x. So let's check. I have 2 times so-called infinity. Bottom, still infinity. So this is indeterminate form. So we could use L'Hopital's rule here. Let's think a few steps ahead though. If I use L'Hopital's rule, the top becomes 2. Looks good. What about the bottom part? The bottom part I'm going to get, so I'm going to do the rough work on the side here. So I'm going to have 2, 1 over 2 square root x squared plus 2x, and then I still have to do the chain rule, plus 1, okay? So this first block here, this is really x plus 1, because 2 can be cancelled. And then I'm going to have that common denominator swinging back to 2 square root x squared plus 2x over x plus 1 plus, and then I need 1 multiplied by this. It looks very complicated, right? And then maybe I can keep applying L'Hopital's rule if I need to. but that square root of x squared plus 2x will give me a lot of square root of x squared plus 2x as I take the derivative. Well, if I go back to the original line that we have arrived at here, what I do notice is one thing. I have a bunch of x's. I have 2x at the top. I have x squared. I have x. I have x. So is there a way to simplify some of these x's? What if I divide every piece here by x, or multiply them by 1 over x? Let's see. So the top is easy, is 2. Now the second term is easy, x over x is 1. When I divide square root x squared plus 2x by x, inside the square root, now I'm actually dividing by x squared, right, of the stuff inside the radical. So here I'm going to have 1 plus 2 over x. Okay. How does that look? So instead of using L'Hopital's rule here, we can actually further simplify our rational expression. And so when I evaluate this limit, the only place that I need to worry about here in this case is the 2 over x here. But I know 2 over, well, a really big number near infinity is 0. And so I have 2 over, really, 1 plus 1, which is 2 over 2. The answer is 1. As a result, the horizontal asymptotes is y equals to 1. Make sure you write it as an equation of a line.